Hello, my name is Vladimir Korikov, and this is the Domain-Driven Design in Practice course. In this module, we will introduce the second bounded context in our application. Along the way, we'll discuss the differences between bounded contexts and subdomains and how they relate to each other. We will also talk about how to choose boundaries for them and how to perform context mapping. We will look at different types of physical isolation for bounded contexts, how they communicate with each other, and finally, we'll discuss the guidelines for using code between them. In the previous modules, we ended up with a snack machine model. Now we have given a new task: create another model, at this time for an automated teller machine, ATM. This model would allow the users to withdraw cash using their bank cards. Just as with the snack machine, here we'll leave aside such details as how exactly card operations are performed or how the ATM dispenses cash. Our focus area will be the business rules behind this model. So what are the requirements for this new task? First of all, the ATM must give the users cash they requested. In return, their bank card should be charged the worth of money dispensed plus a 1% fee. Also, the model must keep track of all money that was charged from clients. To solve this task, we'll introduce a new bounded context. We'll discuss the reasons for that shortly. For now, let's take a closer look at the notion of bounded context. Bounded context is a central pattern in domain-driven design. It stands for separating the model and explicitly drawing the boundaries between its pieces. The reason for such separation is that as your application grows, it becomes harder to maintain a single unified model as it becomes larger and more people get involved into the development process. Big models bring significant communication and integration overhead with them. Bounded contexts help reduce that overhead. There are several attributes that belong to the notion of bounded contexts. First of all, they act as a boundary for the ubiquitous language. It means that the language we use for communicating with domain experts and naming classes in our domain model should be consistent and unified only within a bounded context. At the same time, the naming doesn't have to be consistent across different models. Two bounded contexts can hold entities or value objects with the same name, and they can be completely unrelated to each other. That's perfectly fine. You can think of bounded contexts as if they were C# namespaces for the classes in your codebase. Two namespaces can hold any set of classes, be they intersecting or not. For example, the snack machine bounded context could have a class named composite element, which represents a replaceable item in a machine. The ATM bounded context at the same time could have its own version of that class with its own set of attributes and business rules. These classes, despite the same name, should be viewed differently as they reflect different concepts. Another important attribute of bounded contexts is that they span across all layers in the onion architecture. It means a bounded context is not something you can point out on this diagram. Each of them is represented with its own onion, so to speak. So if you decide to introduce a new bounded context, it should have its own set of entities, repositories, factories, application services, and all other layers from the onion architecture. And finally, it's important to explicitly state the relations between bounded contexts. That's where context maps come into play. A context map is a map that renders the bounded contexts in your system and the connections between them. If you want to see an example of a context map, I recommend you to watch this talk given by Eric Evans. We will draw our own context map later in this module. There is another concept in domain-driven design, subdomain. It's important to understand the relation between subdomains and bounded contexts, as they are often mistaken by programmers. There are two central elements when it comes to building a software project: a problem and a solution. The problem is the reason why we are creating the project, the thing we aim to solve with it. The solution is the actual artifact of our efforts of trying to solve the problem. So the differences between the two concepts is that subdomain belongs to the problem space, whereas bounded context to the solution space. In other words, a subdomain is a part of the whole problem, a part of the problem domain. A bounded context at the same time is a part of the solution for that problem. Subdomains and bounded contexts are best related to each other as one-to-one, meaning that ideally every subdomain should be covered by exactly one bounded context. It's not always possible though. Let's say, for example, that you've come to a legacy ERP project which you need to enhance to address new requirements for the sales subdomain. If the existing codebase isn't covered by automated tests, it might be scary to change it, so you might decide to add a new bounded context and separate it from the existing codebase by an anti-corruption layer. In this case, you end up with two bounded contexts that cover a single sales subdomain. It's a good practice to avoid such situations though, because the code base is overall easier to maintain and understand if there is a strict one-to-one relation between subdomains and bounded contexts. So in the example above, there should be ideally a single sales bounded context. In our case, we have two subdomains, Snack Machine and ATM. As we are working on a greenfield project, meaning that we don't have any legacy code here, it's easy for us to adhere to the guideline and create a single bounded context for each subdomain. It's important to keep explicit boundaries between bounded contexts, but how to define them in the first place? How to draw a line between one bounded context and another? As I mentioned earlier, the best way to do that is to adhere to the one-to-one guideline. In other words, create a separate bounded context for each subdomain. So the question boils down to how to define a subdomain. A subdomain is usually not something that is defined by us developers. As the notion of subdomain refers to the problem space, it is often defined by customers and domain experts. The boundaries for subdomains usually come up naturally during the talks with them. For example, they might mention that they want to build a sales prediction subsystem to help the company stabilize its revenue, or they want a support subsystem to decrease the expenses related to the customer support activities. All these are signs of separate subdomains, so in most situations you just need to carefully listen to the domain experts. However, this approach might not work in some cases, as you need to take into account other factors as well. The first one is the size of the team. If your subdomain is too big and that causes the team working on it to grow more than, say, 6-8 developers, it's a strong sign you need to separate the bounded context in two and form an independent team for each of them. The second factor is the size of the code. Even if your team is small enough, it might be that the code in a bounded context grows enormously so that it becomes hard to manage its complexity. In this case, you might also want to depart from the one-to-one guideline and create two bounded contexts for a single subdomain. The general rule of thumb here is that the code of a single bounded context should fit your head, meaning that you shouldn't have a lot of trouble understanding it. In my experience though, it rarely happens and the one-to-one guideline works just fine in most situations. Alright, we discussed situations where there might be several bounded contexts for a single subdomain, but what about the opposite? Can a single bounded context cover several subdomains? For example, in our application, the Snack Machine and ATM subdomains are pretty small. Doesn't it make sense to solve those problems with a single bounded context? It's true that in our sample application there is little code in bounded contexts. For example, the Snack Machine model consists of only two aggregates. Nevertheless, even if you are able to cover two subdomains with a single bounded context and still keep it succinct, I recommend you to adhere to the guideline and still create two separate bounded contexts for them. Just make sure the subdomains they cover are indeed distinct ones and not parts of a single subdomain. The reason here is that bounded context segregation is a logical one. Whether or not to keep them separated physically is a different question. So even if you do create two bounded contexts, you don't have to create separate sets of Visual Studio projects for them right away. You can carry the code together while it's small and thus keep the maintenance overhead low. We will talk about the degrees of physical isolation for bounded contexts later in this module. The last guideline regarding boundaries for bounded contexts is how they relate to the development teams working on them. It's a good practice to keep the team's boundaries aligned with those of bounded contexts. It means that while one team may work on several bounded contexts, there shouldn't be a situation where two teams work on a single bounded context. It would lead to communication issues and increased maintenance costs. Let's draw a map for the context we have in our application. But before that, let's see how the structure of the ATM bounded context looks like. It will consist of a single aggregate with the ATM entity inside. As the ATM needs to dispense cash, we need to represent that cash somehow, and we already have a suitable class for that, MoneyValue object, which we can use in the ATM entity. Another field here is the money charged field, which will indicate the amount of money charged from the client's bank cards. So now we have a situation where the same value object, MoneyValue object, is used in both bounded contexts. That means there is a shared kernel between them. So our map goes like this. You can see the two bounded contexts use a shared kernel and don't interact with each other, so we can say there is a separate ways relation between them. That kind of relationship actually indicates no relation whatsoever. It's important to remember that such map should reflect the actual state of affairs, not the desired one. If the bounded contexts in your application interfere poorly, for example, one of them has become a big ball of mud and starts affecting other contexts, show it with such diagram. It will be a good starting point on the way to fix the situation. If you see that one of the bounded contexts decays, meaning that the code in it is a mess, you might want to protect other bounded contexts from its impact by introducing an anti-corruption layer. As I mentioned earlier, logical separation of bounded context is orthogonal to the physical isolation. There are several degrees of such isolation you may employ, and each of them has its own pros and cons. The first one is keeping the bounded contexts in the same assemblies, but in different namespaces, so basically just creating separate folders for them. Note that although with this type of isolation you keep the code of the bounded contexts physically close, you still need to maintain proper separation and don't allow them to infiltrate to each other. Boundaries should be preserved regardless of what type of isolation is chosen. Such degree of separation also means you share the same database instance, but again, entities in different bounded contexts should be stored in different tables. If you use SQL Server, it's a good idea to define separate database schemas for each bounded context to make this distinction more apparent. The second type of isolation is extracting the bounded context into separate assemblies under the same solution. Here, for example, you can see two solution folders for bounded contexts and a separate project for the shared kernel. Note that each folder contains its own UI and logic assemblies that regard to a certain bounded context. The third type of isolation is separate deployment. While the first two types imply the bounded context work in a single physical process, this type of isolation means you deploy and maintain them as separate applications. The source code is stored separately, and there are separate database instances for each of the bounded contexts. This type of isolation is often referred to as microservices. The topic of microservices is out of scope for this course. If you want to learn more about it, I recommend you to read this article. It's important to understand the benefits and drawbacks that each of the isolation types entails. The benefit here is that the greater the physical isolation is, the easier it is to maintain proper boundaries between bounded contexts. You are less likely to violate them if the bounded contexts reside in separate assemblies or even in separate solutions. At the same time, the more you isolate your bounded contexts, the more maintenance overhead this isolation introduces. It's harder to deal with separate assemblies in your codebase than it is with only one, and it's even more difficult to handle separate deployment of them in case the third type of isolation is chosen. The guideline here is that you should be pragmatic about the degree of isolation you choose and introduce greater physical separation only when the benefits of it is justified. If your bounded contexts are small enough, it's just fine to start with the first type and move forward only when you feel the code gets bigger and it becomes harder to keep it clean without introducing additional physical boundaries. In our application, we will adhere to the first type because we don't have large amounts of code in our bounded contexts. This is how it looks like in practice. You can see there is a separate folder for the snack machine context with all classes related to it. The ATMs folder is empty because we don't have any code for the new bounded context yet, and the shared kernel contains a single money value object. Note that we also have a folder for common base classes and the other one for utilities. They are shared by all bounded contexts. We will talk about sharing code between bounded contexts later in this course. Also note that we have the same kind of separation in the UI project, two separate folders for each of the bounded contexts. The way entities in different bounded contexts communicate with each other depends on two elements, the type of isolation chosen and the relationship between them. Let's take the first two isolation types, the types that imply you host bounded contexts in a single process. In this case, the communication pattern depends on whether or not there is an anti-corruption layer between the bounded contexts. If there is none, entities in these bounded contexts can just call other entities' methods directly. Also, the communication can be performed via domain events, which we'll discuss in the next module. In case there is an anti-corruption layer, the things get more complicated. An anti-corruption layer usually means that developers working on one bounded context don't want to interfere with the concepts from another bounded context. It's often the case if that other bounded context has become a big ball of mud, or in other words, a mess. Another use case for introducing such a layer is working on a legacy project where you want to keep the new code isolated from the concepts in the existing code base. Regardless of the actual reason, the presence of an anti-corruption layer means that you cannot just allow entities in your model call entities from the other bounded context. You need to introduce a proxy between the two models which would handle all translations for them. So whenever you need to perform a call, your model calls the proxy instead and gets a response which is formed in a way that is familiar to it. In case the third type of isolation is chosen, meaning that two bounded contexts are hosted in separate processes, the communication goes through the network. For a direct call, it is usually an HTTP call using REST or SOAP protocol. For an event, some sort of a message queue is used. In this situation, you don't have to create an anti-corruption layer between the two bounded contexts, because this messaging mechanism essentially acts as such. An important topic which is often gets misunderstood is code reuse between bounded contexts. It might turn out that there is some code which is common for two bounded contexts and which can be factored out and reused in both of them. The first temptation in such situation is to perform the extraction in order to comply with the don't repeat yourself principle. On the other hand, we have a guideline which says there should be strict boundaries between bounded contexts and developers should not allow concepts from one context to infiltrate to another. So how to deal with this conflict? To answer this question, we need to define different types of code which can be a potential subject for reuse. The first type is code that carries business logic. Such code should never be reused unless it has the exact same meaning for all bounded contexts involved. For example, you might have two bounded contexts, sales and support, which both contain a product entity. It may even be that these entities have some behavior in common. In this case, you still need to create separate entities for them in both bounded contexts and store them in distinct database tables. The reason here is that despite the fact these entities have some commonalities, they still represent different concepts. The sales perspective on what a product is not the same as the support perspective on it, even if that is the same physical product. You shouldn't try to merge the two concepts into a single entity. At the same time, two domain classes might have the same meaning for different models. For example, both snack machine and ATM bounded contexts have identical perspective on the money value object. It represents the same concept for both of them. If this is the case, you do need to reuse it by extracting this class into a shared kernel like we did previously. It's a good idea to treat that kernel the same way you treat a bounded context and strictly maintain its boundaries. The second type of code is domain-based classes, such as entity, value object, repository, and so on. They don't contain any business logic themselves, but are still used by the actual domain classes in your bounded contexts. The answer to the question whether or not to reuse such code depends on the team configuration in your project. If you have the same team working on two bounded contexts, then it's a good idea to reuse domain-based classes. On the contrary, if there are separate teams working on those models, they are better off to have their own implementations of those base classes, even if those implementations are identical. The reasoning behind this guideline is that despite the fact the base classes don't contain any business logic, they still are an additional point of coupling between the models. It is fine to have that point if you have a full control over the bounded contexts that use these base classes. Otherwise, it becomes a burden to maintain consistency in changes that are made by different teams. So, one set of base classes per each team, regardless of how many bounded contexts they are used in. In our application, we use the base classes, because we are the only team working on this project. The third type of code is utility code, code that doesn't contain any domain logic, but rather represents some useful helper methods. The guideline here is roughly the same as with the domain-based classes. If a utility is small, such as Session Factory in our application, just duplicate it so that each team has its own set of helper methods. At the same time, if such code gets bigger and you see it can potentially provide a lot of value to all teams in your company, create an internal open source project out of it. You can extract it to a separate project and make it publicly available to all teams in your company, but that should be something really useful, not just a set of random auxiliary classes. Overall, try to avoid reusing code between bounded contexts as much as possible, especially reusing the code from the domain layer. Extract a domain class to a shared kernel only when all bounded contexts involved have the same perspective on what it represents. Alright, we're now ready to start implementing the second bounded context, the model of ATM. It will be simpler than the snack machine model. The only functionality it should contain is the ability to give the users cash in exchange for their bank card's balance. The ATM also needs to keep track of all charges made. This is how the implementation will look like. You can see it's a single entity with two fields, one for the money inside and the other one for the money charged. We'll start off by working on the ATM entity. Note that for this project I've chosen the first type of bounded context isolation, because the bounded contexts themselves are pretty small at this point. It means that we will gather all classes for the new bounded context in a separate folder. We won't create new Visual Studio projects for it. Alright, creating a new class, ATM. This would be an aggregate root, so I inherit it from the aggregate root base class. The entity will contain two properties, money inside and money charged. And I'm adding a method for taking money from the ATM. Now let's add some unit tests. Creating ATM specs. Good. With the first test, we'll verify that the money inside the machine decreases and that it accounts the amount of money charged from a user. Creating an entity. In order to check the money inside the machine changes, we need to load it there first, so I'm calling a load money method here. This method doesn't yet exist, we'll add it shortly. Assuming there is $1 inside the ATM, I, as a user, should be able to take it. After that, the amount of money inside must turn to 0, and the amount of money charged should be $1.01, because the commission for withdrawal is 1%. Creating the load money method. This method will just add whatever money we pass it to the money inside property. We can see it fails, that's because we need to initialize the money inside property with an empty instance. Okay, now the test fails for a good reason. It expects the money inside to turn to 0, but sees there is still $1 inside. Let's implement the takeMoney method. Just as with the snack machine model, here we allocate the required sum and extract it from the money inside property. To calculate the charge amount, we need to compute the amount with commission and add it to the money charged property. Perfect, the test is passing. Let's implement a little bit of refactoring. Let's extract the commission rate to a constant and also introduce a using statement to avoid specifying the money class here. And let's do the same in the test. Good. There still are some requirements we need to take into account. For example, what if we try to take a single cent from the ATM? Should the commission be still charged in this case? And if so, how much should it be? Also, are there any rules for rounding the commission? For example, what if a user takes $1.10? Should the commission be 1 cent or 2 cents? These are the questions we should ask the domain expert. Let's say the expert replied that there should always be at least 1 cent commission for any withdrawal operation and the commission itself should be rounded up to the next cent. And now, as we have this knowledge, we can reflect it in our unit tests. With this test, we ensure that the commission is at least 1 cent. You can see we load a cent into the ATM and take it back from it. The money charged should be 2 cents in this case. This test will make sure the commission is rounded properly. When we try to take $1.10, the machine should charge 2 cents as a commission, $1.12 overall. Both tests are failing currently. Let's implement the required functionality. So, in order to comply with these two requirements, we need a more sophisticated calculation algorithm for the charge sum. We cannot just multiply the amount by commission rate. Here is the function we will use for that purpose. As you can see, it calculates the raw commission amount first, and then determines if the amount contains a fraction which is less than a single cent. If there is such a fraction, the method replaces it with a cent and returns the overall amount with the commission. We can replace this code here with a call to this method. Good, the test has passed. The last thing we need to add is validations. We will use the same pattern we used previously. We will create a separate canTake method, which will return an error string in case any of the preconditions are violated. So what are they? First of all, we shouldn't be able to request 0 or negative sum, it just doesn't make any sense in the context of ATM. Secondly, we need to check that the money inside the machine is sufficient to address the user's request. And finally, we need to check that the machine has enough change to pick the required sum. An empty string here would signalize no errors. After we enumerated all preconditions, we can use them in the takeMoney method. And of course, it's a good idea to check these edge cases with unit tests. Very good, the ATM domain entity is ready. Now, as we have the domain class for the new bounded context ready, let's adjust our persistence layer. Here's the new ATM table. Note that once again I inlined the data for the money value object inside the ATM entity. Besides the money value object, we also have a money charged decimal column. I created a new ATM row for the test purposes, and I also added a new row to the IDs table. Alright, we are ready to define the mapping between the entity and the database table, creating a new class, ATM map. Inheriting it from class map, the mapping here is pretty simple: the ID property, the money charged property, and the money inside value object. Good. The last thing is the repository, adding a class, ATM repository, and inheriting it from repository base class. This class will be empty because all required functionality resides in the base class. That's pretty much it. The last remaining thing here is the user interface. At this point, we can define the user interface for our model of ATM. I added a XAML view beforehand, and this is the view model for it. You can see it contains only a caption and reference to an ATM entity for now. We need to add the remaining functionality here. This is how the UI looks like currently. As you can tell, it is not functional because the view model is not yet defined. So in order for the user interface to display the actual values behind the ATM, I need to add two properties here: money inside and money charged. And now if I run the application, you can see all the values are filled out. We have the coins and notes inside the machine, as well as the overall amount of money inside and the amount of money charged. The idea is that we simulate the process of withdrawal by inserting the required sum in this text box and clicking on the Take Money button. You can see, although the values are displayed correctly, the interface doesn't react on the button clicks. To perform the actual withdrawal, we need to define a command, like this, and instantiate it in the constructor. It will execute the Take Money method, passing it the required amount to dispense. Note this predicate here. It's a quite handy feature of WPF commands, which allows us to define in what circumstances the command can be executed. In this particular case, we indicate that the command can be executed only when the requested amount of money is more than 0. In this method, we will follow the same steps as in the snack machine view model. We are asking if an ATM can dispense the sum for the user. If not, notifying the view and returning from the method. Otherwise, taking the money, saving the ATM using the repository, and notifying the view about the success of the operation. To display a message for the user, I need this property. And now I can define the notify client method. You can see it sets the message and notifies the view about two properties the view depends upon. We also need a repository. Instantiating it in the constructor. Good. Let's try to withdraw the money now. I'm taking $1. As you can see, the number of $1 bills inside the machine decreases, and the money charged is set to $1.01. If I restart the application, all parameters are still in place, which means that the ATM was successfully saved to the database. The last thing remaining here is actual charging the value of cash dispensed plus 1% commission from the user's bank card. We won't be writing the actual code for this here, but I wanted to show you the overall idea of how to do that. The operation we are about to perform resides in an external service, and the best way to work with external services is create a proxy class that wraps it with an API which is consumable for our application services. Here's such a proxy class, Payment Gateway. It's just a stub for a real gateway, but a real-world implementation would probably have similar interface. It's important to understand that in properly isolated model, domain classes shouldn't work with such gateways. The layer which is responsible for that is application services, view models in our case. So let's define a payment gateway here and instantiate it in the constructor. To use the gateway, we need to know the amount to charge. In other words, we need to sum up the amount of money dispensed and the commission. We already have such method in the ATM entity. All we need to do is make it public. And now we can calculate the amount and charge the payment. And again, although the payment gateway doesn't do anything at this point, this code shows how you can approach this task. Alright, we have the ATM model implemented and working as requested. In this module, we discussed bounded contexts. Bounded contexts indicate boundaries between different models and ubiquitous languages used in them. We talked about the relation between bounded contexts and subdomains. The distinction between them is that subdomains belong to the problem space, whereas bounded context is the solution for that problem. We discussed the one-to-one guideline. You should try to create a single bounded context for each subdomain in your system. But keep in mind that it's not always possible. There are 3 reasons why you might want to depart from this practice: legacy project, large codebase, and large team. We talked about the importance of drawing a context map between bounded contexts. The main guideline here is that it should reflect the actual state of affairs, not the desired one. You learned 3 types of physical isolation of bounded contexts. Keep in mind that while your codebase is small, it makes sense not to separate bounded contexts physically and just keep them in a single assembly. As the project grows, however, consider extracting different bounded contexts out of it to separate Visual Studio projects or even to separate microservices. At the same time, make sure you maintain proper boundaries regardless of what type of physical isolation is chosen. We discussed communication between bounded contexts. It depends on the type of isolation you've chosen and whether or not there is an anti-corruption layer between the contexts. We also talked about code reuse. The main rule here is that you should avoid reusing code that represents domain logic. In the next module, we will talk about domain events and 2 different ways of working with them.